That's fine.
Wow, I've not had I'm too used to the school's buffalo chicken dip. That is fire.
Oh yeah, it's next level. So first of all, Sean, as you're listening to this, thank you for the brownies. We love you.
Hi, Sean.
We have your Valentine's in a lid. So
Evidence of our love.
yes.
This proves we love you.
I hope he watches this tonight. Anyways, it's kind of odd. And like I said, you guys are the best. This class is amazing. So I appreciate you guys. I appreciate your hard work, your work ethic, because we have been working hard. Because somehow we are ahead still by 4 days from last year.
I don't think you do nothing to that.
Huh? No. Because remember, each day that I have notes on my plans from last year is 2 days worth here.
That's true.
So we're slowly kind of losing a day, like a week, but it's fine. We're good. We're completely fine. The odd thing is that this is the second to last packet of notes.
Whoa.
If you think about that. Because this is Unit 8. So I'm basically doing a whole unit in a packet. This is not all the notes for the chapter. It's the majority. So we'll go over kind of a general stuff for the chapter, and then this is chapter 14 and 15, I believe. Is that what it says?
Yeah.
Yes. Chapter 14 and 15. Only one unit left after this. This is historically what we're about to start, the hardest unit of AP Chem.
Oh,
I've heard of this unit.
So,
I heard Alan
But-
got the highest grade on this.
what's that?
I heard Alan got the highest grade on this last year.
Alan did really well on this test. But I also have to rewrite the test again because it's for a double period. Anyways, so the main thing that people historically struggle with in this chapter, and it almost becomes like a cuss word, is buffers. So if you've talked to anybody in AP Chem last year and you say buffers, they'll be like, no, all right? But
Call Sophia right now.
I've got some new ideas for this year. All right, I always teach it better than the year before. And I've got some new ideas of how to teach it and make it even better. But I don't think we're talking about buffers today. Today, we're just going to start out with some general, almost review of stuff that we should know and a little bit of new stuff. And we're going to get a new K, since we don't have enough Ks already. Another K, yes.
Another day, another day.
Another day, another K, yes. So, the first thing that I wanted to do was just kind of redefine acids and bases. And we're going to learn there's actually two types. There's two types. So, acids can be defined in simplest terms in terms of proton transfer. Because if you are an acid, you're going to be donating a proton. So, their strength, an acid's strength, in terms of ionization, or dissociation. Do you guys remember that word?
Yeah.
All right. Dissociation. And how they can be sorted into acid, base, conjugate pairs. Is that a sentence? Acids can be defined in terms of proton transfer, their strength in terms of ionization or dissociation, and how they can be sorted into acid, base. Yeah, that's a sentence. Period. Now it is. Now it's a sentence. It was a run-on sentence, but it's a sentence. So right there, that's about three new things. Especially, yeah, we're done. All right? Especially the conjugate pairs, but we're going to talk about it. So here are the two definitions that essentially mean the same thing. The first one is an acid defined as a Bronsted-Lowry acid. So the simple definition of a Bronsted-Lowry acid is a proton, or I'm going to put hydrogen ion in parentheses. And what is the hydrogen ion? It's just H plus. It's a proton donor. That is the simplest definition of an acid for a Bronsted-Lowry acid. A base is a proton acceptor. Yeah. However you want to say it. Acceptor, receiver, either one is fine. Now, not to be confused with the Arrhenius definition of an acid and a base. And like I said, these are the same thing, just different terms. So I could see this being like a multiple choice question on the test. So, not my test, the AP test. And an Arrhenius acid is a substance that dissolves in water. So this is about what it does in water. To produce, not produced. Talk like my grandfather. Which, tell me something good Tuesday is today. It's Kevin times, obviously. And I took my grandparents out to dinner last night.
Where did you go?
So Denny's.
Oh.
That's a very 85-ish year old place to
Ooh, did
like.
they get to use their AARP discount of 15%?
Well, my grandfather's military, so I think he got his for free.
Oh, wow, okay. Jeez.
So,
Blow me
but
out of the water.
it was still $70.
Sign up for AARP.
There were 6 of us with my daughters.
Oh. I thought it was just
But-
you and them.
But like to spend $70 at Denny's felt weird.
That's
does feel weird.
Like when I was in college, I would spend like $5 on a lumberjack slam. Like, and I still got the lumberjack slam last
This
night.
gets me 15% off at every Denny's in the continental United States.
Wow.
Probably also lets me buy
Continental.
Wow. Wow. I need to become a member. I need to become a member. Anyways, this is I do this to myself. I do it to myself. An acid is a substance that dissolves in water, sorry. To produce this next thing is really important. Hydronium, which is H3O+.
That's crazy.
Hydronium is going to be something that you're going to be dreaming about because we're going to be talking about it so much. Because hydronium used to be what?
water.
Water. So hydronium is water that accepted a proton.
Does that mean water's a base?
It's super water.
Stay tuned. Water's both, actually. We'll talk about that. A base is a substance that dissolves in water. To produce what? OH minus. OH minus also used to be what? Water. Right? So water can lose a proton, water can gain a proton. Either way, it depends what it's with. It depends what it is with. So water, we'll see what that's called later. So, for example, let's do a strong acid. So here's HNO3, which is AQ plus H2O. What's the state going to be for H2O? L. I'm going to do some states here just to remember what we're doing. What is that going to give me?
H3O?
Well, first of all, you have to ask yourself, is water going to act as the acid or the base here?
Probably the base.
The base, why?
We have the acid.
Because HNO3 is a strong acid,
Strong.
right?
Oh,
So
so
we do that
that's
strength.
We're gonna start to have to use those.
It's
Yes.
the buffer of the acids.
I was
So-
thinking we didn't have to use those.
This is, yeah, well,
That was
it's
so
even
crazy.
more important now.
Yeah.
All right? So we talked about acids a long time ago, now it's going to matter. So this is going to give me H3O plus, AQ, plus what? NO3 minus, just a nitrate ion, also AQ. So to start, this was my acid, water was my base, and now on the other side, I now have H3O plus. That is my conjugate acid. And this NO3 is my conjugate base. I did not write that out, but conjugate is spelled CONGUGATE. It's also up here. All right? Up here, conjugate. So these are my conjugate pairs. We'll talk about it. I'm probably going to talk about it more, but I'm going to go ahead of myself here. The conjugate of a strong acid is always a weak base. Is always a weak base.
Crazy.
The conjugate of a strong base is always a weak acid. So this is an acid on this side. My conjugate acid is on this side because now this has an extra what to give away if it wanted to?
Proton.
Extra proton. NO3 wants to gain a proton. That's why it's now a base. So here's my acid, conjugate acid, base, conjugate base. Are you okay with that? For the first starters.
Yeah.
Okay, can somebody grab the door? Thank you. In this example, water acts as a base by accepting, I'm keeping my acceptor here, accepting a hydrogen ion. HNO3 acts as an acid by donating a hydrogen ion. The hydronium ion is a product. Many times, most of the time, what I'm going to do, and what AP Chem even does, just the proton, which is H+, will be written instead of the whole hydronium. Because we really don't care about the rest of that molecule. All we really care about is H+. And you'll see why later. All right? Hydronium is not really used a lot because it's the same thing. So H plus, H3O plus can kind of be interchanged. Marin.
What's the difference between hydronium and hydroxonium?
Did I write it?
Yeah.
Yeah, that's wrong.
Okay.
Oh, okay.
There we go. Hydronium is barely used. All right.
So,
Good catch.
I was on the
Hydroxonium is nothing. It's nothing. Here's example 2. So here I have NH3, which is AQ, plus water, H2O, which is a liquid, in equilibrium. Notice I'm saying in equilibrium with NH4 plus OH minus. So this is also AQ. So, first of all, what did NH3 do?
Gained a proton.
It gained a proton, which means NH3 had to start out as a, no,
No, base.
this is a base, all right? Ammonium was a base here because it accepted, which means in this case, water acted as an acid. So over here, NH4 is my conjugate acid, and OH is my conjugate, excellent, is my conjugate base. So on the other side, they should match. So you're going to be able to do like a conjugate acid-base pair. I guarantee that'll be one of the problems you do eventually in the book. It's going to say what's the conjugate acid, what's the conjugate base. In fact, they'll probably just give you the products. You'll have to write. They'll give you the reactants. You have to write the products and then say what it is. Which you guys can do that. Here, water acts as an acid. Water acts as an acid by donating a hydrogen ion, and NH3 acts as a base by accepting a proton. OH is the other product of the reaction. So wait, we've been talking about this. This means water can act as an acid or a base.
What?
Which is super, super important. This is why water is considered, there's a term for this, amphoteric. A-M-P-H-O. What did he say?
I spelled it.
Also, part of the reason, right? It makes sense why water is a universal solvent because it can dissolve acid or base. It's amphoteric. I put a bunch of stars there because that means it's super important.
Fan of water.
So water can be an acid or a base. So, more on acid-base conjugate pairs. Conjugate acid and base pairs are related. They're related by a difference of a what? Hydrogen ion. Same thing, right? By a hydrogen ion on either side of the equation. On either side of the equation. So, if we look back to the example and assume that it proceeds in the forward direction, the one we just did, then NH3 acts as a base, this is just a little review, by accepting a proton to form NH4+. So acid bases, Bronsted-Lowry acid donates a proton, and Arrhenius acid dissolves in water to make a hydronium ion. So you have to know the difference between those two. Flip it. In the same reaction, if it went backwards, because remember, these are going either way, still, NH4 would then act as an acid by donating, NH4 plus, by donating a proton. This makes them an acid-base conjugate pair. So that is what an acid-base conjugate pair is. It's called a conjugate because it can go either way. Depends if it's going forward or backward. Or for your view, forward or backward. I did that so it's like from your point of view, forward, backward. That's next level. Next level. Strengths of acids and bases. It's super important now, this chapter. All right, it's super important because you're gonna have to know if an acid completely dissociates in order to do your what right? Your ice.
We're icing.
All right. Oh yeah, we're icing everything at this point.
That's all right. I don't
Yeah.
like ice.
All about ice. So, a strong, ice is nice. A strong acid completely dissociates. A strong acid completely dissociates. Let's pause now.
Universal solvent.
Let's pause now to write down all of the strong acids
Good. That was one.
because you need to have these memorized.
Yeah.
You got to know these. Hydrochloric acid.
Wait,
What?
I don't know.
What?
Hydroiodic, is that one?
What?
Hydroiodic.
Hydroiodic. Yes, someone had that on their box. Who had that? Or no, that was my Valentine.
Hi.
Yes. Hydroiodic acid is one. What else? Anyone know?
Hydrofluoric.
Hydrobromic.
What was it?
Hydrobromic. I'm just going to keep listing them. Sulfuric. Nitric. And lastly, HClO4. I think is that perchloric? Why am I struggling right now? Everyone at the periodic table? What is that? What's ClO4? Why can I not think? Is that perchloric or chloric?
They basically get rid of all the
It's either chloric or perchloric. Why is nobody Googling this right now?
Oh.
I can't remember.
Perchlorate ion.
I think it's chloric.
ClO4.
Perchlorate.
So it's perchloric. So perchloric acid is also, this is straight, 1, 2, 3, 4, 5, 6. If you look at 8.2, all right, over there, it lists, well, if you saw like the details, it lists out these 6 strong acids. You gotta know them, all right? I'll probably ask you at some point on a test. What are the 6 strong acids?
I'll just start.
You've gotta know. Okay, so for example, moving on. A strong acid, let's do HCl, and a strong base, B. All right, strong base, B, any base. In the following, reactions go to completion or completely to the RHS, which is going to be right-hand side,
Yeah.
obviously. Right-hand side to produce large numbers, this should say of what? What's it going to make? H3O plus and OH minus. It's going to make both of those. So here we go. Let's write out the equations here. I have HCl, which is AQ, plus water, H2O, which is a liquid, is in equilibrium with H3O plus what? Cl minus. Cl minus. Or I could just write base B. All right? Let's just say I did B for the base. If I go B plus H2O, what am I going to get?
OH minus.
I'm going to get OH minus plus
B plus. No. Yeah.
CB plus. CA plus.
BH plus, right? Gotta be BH plus. Nice job, Allison.
It's conjugate, but we're dissociating.
Well, I know that this has to be a proton. This should probably be B minus. That would make more sense, right?
No, but then it wouldn't.
No, it doesn't have to be B minus.
Okay.
All right, nope. It doesn't have to be a minus because it has to be balanced because I have a negative and a positive. It'll be BH plus. So that's just kind of a general form.
I'm going to the dentist today.
Same.
This is not.
Oh.
Base.
Actually, it's a good day to go to the dentist because you're all that sugar cleaned.
Excuses. I
My
have
appointment is
excuses.
at 2.
If I had sugary teeth yesterday night, no excuses. Today, sorry, Dr. Root, Valentine's Day.
See, but here's the thing. I don't think it matters one day what you do for the dentist.
Yeah.
It's a lifestyle. Brendan, question. Okay. If the first reaction,
Who would have worse starburst?
what am I saying
It
here?
is a lifestyle.
If the first reaction laws
Goes?
lays, that makes more sense. I should not say laws. If it lays almost 100% to the right-hand side, then HCl is a very strong acid, which we know it is, compared to H3O plus, which is the potential conjugate acid in the other way.
Is it blank?
Very strong acid. Is a very strong acid.
Why is it comparing to H?
Why? Because H3O plus would be the conjugate on the other side.
So you're just saying it's stronger than H3O plus?
Yeah,
Okay.
much stronger. HCl wants to get rid of that hydrogen way more than H3O plus. Because the conjugate is weak. The conjugate of a strong acid is a weak base.
And it mostly favors the.
Correct.
Okay.
Correct. You got it. It's also true that the conjugate base of HCl, which is going to be Cl minus, is a very weak base. And we talked about this. I got ahead of myself. So the conjugate base of a strong acid is a weak base. The conjugate base of a weak acid would be a strong base. You got it. This is true of all conjugate pairs. This is true of all conjugate pairs. Do you guys see what is going on underneath this? Do you see that? Lower on your page?
Oh,
Do you see that?
yeah, weak and strong.
It's in color.
What?
Oh,
What?
nice.
Whoa. No.
I literally had to copy this page. I had to print this page separate, take a page out, and put that in to make it in color.
Wow.
Wow.
Because if you look, there's nothing even on the back of that page.
Yeah.
So I individually stapled all of
Well,
this.
that's why it was.
Yeah, I know.
Wow.
Anyways,
So
I was very excited about that.
I love color.
So this might be the difference between this year and last year. You guys will understand buffers because of this picture.
Yeah, right.
Watch as we actually do.
Whereas a strong component of conjugate pair will always be accompanied
I would not be interested.
accompanied by an equally weak partner on the other side. Hopefully that's not how your life ends up being.
Wow.
Right? Marry somebody if you decide to get married of like equal.
Opposites attract.
Opposites do attract.
But like,
But-
you can't. You gotta be equal.
Whoever you pick, make sure it's someone that can like compliment you.
You don't want to get dragged down.
Okay?
Right?
That's kind of aggressive stuff.
Isn't that exactly what you were saying?
No, I was just saying, not necessarily get dragged down. I'm just saying, try to pick someone. Is there something we need to talk about?
No, I thought that what you were saying was that because if you married
What?
the weak,
No,
Why
I.
do you assume you're strong, Seth?
weak relatives is equal now. I'm not strong.
I was just saying, pick someone who compliments you equally.
Yeah, exactly.
Yes.
Like if you feel strong, you don't want to like be over like
Why
powering
didn't you
this
say
person.
that you
If you
the
feel
strong
weak,
one?
then you don't want them to like hurt you because they're too strong.
Hurt?
Happy Valentine's Day.
Let's get Sophia over here.
She's
Yeah.
like my interpreter for it.
All right.
Anytime
Moving
we're-
on.
The stronger the weaker.
Weak. Yeah. Which one is she, Seth? Weak acids.
We're destroying
You're the strong one.
Sometimes, like, you'll see, like, it's good that my wife isn't here right now because she'd be like, so what are you trying to say? And I'm like, let's move on. I don't know. I actually don't know.
I don't know. I think you're
I don't
right.
know.
You're right. Take it back.
I actually don't know what I'm trying to say.
Yeah, that's.
I was trying to say something deep. I don't think it ended up being that way. Anyways, so this is what I do. Like, let's keep going. Keep going. Brush it under the rug. Onto the rug.
Very little.
Weak acids, I love you guys. Weak acids and bases, on the other hand, have very little ionization, right? Weak acids don't want to break up. So the equilibria of these lay heavily to the,
Dissociated.
left-hand side. For example, the undissociated form. So if I've had let's just do HA. All right, plus H2O. That's going to be in equilibrium with H3O plus A minus. So this could be an example of a weak acid. Or if I have a base, here's my B plus H2O. We've already done this, but we're going to do it again. This could give me BH plus OH minus. So these are just general forms. I want you guys just to get used to writing out general forms of acid bases on the other side. So take a look at these 4 multi-colored diagrams. So HA is an acid. It's represented by pink, green. H plus is a hydrogen ion represented by green. A minus is an anion and is represented by pink. And water molecules are the white circles. A couple questions I could ask you about these. Number 1, which diagram represents a concentrated but weak acid? That is correct. That was quick.
Right?
Who said B so fast? Were you just saying B?
No, but I looked at the diagrams and actually got them.
You just said.
No, it's not like an educated guess. I actually was kind
uneducated guess.
The answer is B.
Uneducated guess.
Abby's right. So Abby, do you want to explain your answer?
Okay, go ahead.
Okay, well, I said it was, in my head. This might not be right, but I probably got lucky. But the concentrated is because there's the most amount of the H plus ions connected with the least amount of water.
That's it.
Really?
You're right. A weak acid doesn't want to break up.
Freaking clutch.
That is exactly correct. All right, nice job. Don't be surprised. That's a good answer.
That's all
All right, that's right. A weak acid doesn't want to break up. So I've got the weak acid together. Look, here's one that broke.
I'm just crying. This is monumental.
Yeah, that was a great answer. One broke up, but the majority stayed together because it's a weak acid and mostly just water.
What about A?
Yeah, what is it?
Because it's concentrated.
Because this isn't as concentrated.
Yeah.
If we're going concentrated, that has to be less water. Or yeah, less water. This one has this is not a concentrated weak acid.
Oh, okay.
What?
This is a lot of water.
Yes, you got it. Nice job, Abby. That was like boom. All right. Which diagram represents a relatively concentrated but strong acid? C. Why?
Because it's all broken up.
It all broke up, right? It all broke up, and there's not a lot of water. It all broke up, not a lot of water. And then 3, assign relative strengths and concentrations to the 2 remaining diagrams. So what would you say for A? A is a dilute weak acid.
It needs to marry concentrated and strong.
Yeah. Be careful here. D is a
Strong but concentrated.
dilute strong acid. It's a dilute strong acid.
I finally figured out, really quick summary, something you're weak at, you don't want to be double weak, because that's bad. But if someone's like good at something you're bad at, then you kind of even it out, so you help each other.
Okay, I like
That's how I
that.
say it.
That's good. That's
That's
good. That's good.
Take your notes to catch up.
That makes sense. That is good. That's actually good.
Had to get that out before work got back.
Yeah. I'm actually sending the link of these notes to Sophia, so
Sorry, you don't.
You just sealed the
Because
deal.
I know that she'll just listen to what I said and not listen to my explanation, so you don't have to say it.
okay.
She'll be so
All right.
sad.
You're assuming that she won't listen to you?
Me saying
I think she actually would.
You think?
If I said we talk about dating and you and Seth's relationship,
That's, yeah. Yeah, she might if you say that.
I'm not going to. I don't have time for that. I
That's
don't have
good.
time for that.
me saying
Flip it.
me getting this right is just as me saying it was an oil pump. Like those are the two highest moments of this.
I am very proud of you. I am very proud of
I
you.
did that.
It
It was just-
Yeah, I did. First of all, it was great.
So I was talking to my wife about that about a month ago, about the oil pump. And she's like, "Well, draw it." And I drew it. She's like, "That is horrible." So then she started having me just draw random pictures, and she just laughed at me for an hour straight, like
Horrible.
drawing. But like, that's okay. That's our marriage. It's good. Horrible. I'm a horrible drawer. She's a good artist. See?
Weak and strong.
That's what Seth is saying. Bad artist, good artist.
Yes, correct.
Right. So, moving on. We are not making large progress here, but that's okay.
We're
It's
on
balanced.
page 3.
That's true.
This is not bad.
That's not bad. That's true. Note the concentration of H3O plus and OH minus are dependent on 2 factors. Number 1, the strength. The strength of the acid or base, for example, the degree of ionization. So how far does it break apart? The more it breaks apart, the stronger the acid. Or the amount of water present, also known as the concentration of the what? Solution. The concentration of the solution. Yes, you're right as well, Jacob. But it would be the concentration of the overall solution. So this means it is possible to have a dilute, I showed you this on the last page, but still strong acid. And to have a concentrated but weak acid that would have the same hydronium ion concentration. And if they have the same hydronium ion concentration, the pH is also the same. Because pH It's P. Guess what the H stands for? Hydronium. All right?
The H stands for H.
Yeah.
Brandon, if I were you, I'd be looking for someone strong.
So, what? You're going to learn what the P is in a second. Not today, probably, but you will find. Oh, here it comes. Here it comes. I don't know if we'll get to it today.
Are we pushing it?
We're not pushing a P.
No,
We're not pushing P. All right? So here we go. This is going to kind of blow your mind for pH, kind of like brings it all full circle for you. So, the pH scale, that's lowercase p, capital H. The pH scale is used to indicate the relative acidity, this next one is hard to write, or basicity.
There's no way it's a word.
It is. Basicity of an aqueous solution. So, acidity or basicity of an aqueous solution. We'll zoom in just a little bit. Where? That's A Q U E O U S.
This is all vowels.
That's why I'm saying it with my mouth as well. All right. Traditionally, these scales range from 0 to 14, and pH is less than.
7.
We talked about this. 7 are acids, and also pH is greater than 7 are bases. 7 is considered
Neutral.
and that was a run-on sentence. If you look at that. Also, we're going to see later how 7 isn't always neutral. Because once again, the farther you get in chemistry, the more you prove wrong.
Can we just have one thing work?
That's like, it's like this. It's like this.
I mean, until we discover something else.
Guys, we all thought
I mean,
there was 1K, and now we're on like the 7.
I know, we're on like K, like 12. So, when one is asked, are you ready for this? To take a P.
Nice.
When one is asked to take a P, you will never forget what that means from this point forward. To take a P. Because pH, the P stands for the negative log. So taking a P is a negative log. And we already know what the H stands for, the concentration of hydronium. So pH is the negative log of the concentration of hydronium. That is what pH is. So taking a P is the same as a negative log. And so the P is negative log, the H is concentration of hydronium. That is what pH actually is. It's kind of weird. We're not going to call it the negative log of the concentration of hydronium. I mean, that's a lot. It's like, do you want to call it that or just pH? I don't know why they chose P, in all honesty. But when you say take a P from this point on, that means take a negative log.
Well, the P stands for negative log.
Yes, yes. So you can also have POH now, which is going to be the negative log of the concentration of hydroxide. You got it. So we now have POH and we have pH. You didn't even know POH existed 2 minutes ago. All right? But it does. The cool thing is this is not hard. All right? This is not hard. If you can do a negative log, you can do this, which you have a calculator, so you can. So,
Not all of us.
not all of us.
Yeah, Brendan just free hands up.
You're going to...
It's the same as the log.
I mean, this is just like base 10 stuff, right? It's not that hard. Anyways, if you have a strong acid or base, dissociation is assumed to be 100%. Therefore, the concentration of H plus or OH ions can be determined directly from the stoichiometric ratios in the balanced equation and the concentration of the acid or the base. For example, sodium hydroxide, that's a strong base, right? Yes? And nitric acid, our strong base and acid. I have eaten a lot of sugar in the last hour, respectively. I know, this is good notes. This means that when they ionize, dissociation is complete, or it's assumed to be complete. So, if I have 0.01 molar solution of each, that will yield 0.01 molar of hydroxide and 0.01 molar of H. So we are assuming if we start out with a molarity of a strong acid or base, the molarity of its ions is the same. That's key. That's what I'm trying to say here. So if it's a strong acid or a strong base, whatever molarity I start with is also the molarity of the ions.
Is it different for like sulfuric acid since it has H2?
H2,
With that.
it would still be, so that's a diprotic acid. We'll get there.
Okay.
We'll get there. We're talking about monoprotic acids right now. We'll get to that. So remember, H plus, hydronium, same thing, right? Interchangeable. So the major species, you're going to start hearing about major and minor species in a solution of a strong acid or base will be the H3O plus and the OH minus. That's probably a good point to stop for the day.
Good clones.
We'll pick it up from here, and you're going to see why taking the pH of a strong acid or a base is nice.
Oh,
So-
you were gonna say something like.
So let me give you a little preview of where